Okay, so on this one we want to try to draw the shear diagram pretty much by inspection, and then we're going to use the area under the shear diagram technique to find the change in the moment. So this is the technique we're going to use after we find the area under the shear. Alright, let's see what we've got. Let's find some reactions. I know that I have an AY and a BY. Sum of the moments about A is equal to 0. See if we can find those reactions. So I got minus 800 times 1, minus 600 times 3, minus 1200. We have to take that applied moment into account, plus BY times 4 is equal to 0, and I can solve that for BY is equal to 950, and then AY, sum of the forces in the Y, is equal to 0, so AY then is equal to 450. Okay, now we have enough information. We can draw the shear diagram by inspection. AY is equal to 450. Goes up to 450. Goes over here and it goes down 800. So that's negative 800, taking us to a point of 350. So that is negative 350. As it goes through this point, there's no change in the shear, even though you hit this moment. So it's going to stay at negative 350 all the way to here. So I'm just going to keep on going all the way to there. From here, I take a step down another 600. So 350, negative 350 minus 600 goes all the way down to minus 950. It goes from here, and then it goes up 950. You can know that this is the reaction, so it has to go up 950, and it gets back to 0 at the end. And that's most often going to be the case, is that the shear will start at 0 and end at 0, and it may have a reaction at the end which causes it to immediately change, or there could be a force at the end which makes it can immediately change. But in general, what we'll call it is we'll start at 0 and end at 0 on the shear. Alright, now to draw the moment diagrams, let's find the area under the shear diagram. So in this case, this is fairly easy. It's 450 times 1, so there's 450. This one's going to be 350, and that one is 350, and this one is going to be 950. Those are the areas under, and that helps us draw the moment diagram. So again, the moment diagram will increase linearly if shear doesn't change. So we'll get to distributed forces in just a little bit. It's going to go up like that, up to the point of 350. Then it decreases 350. So I'm sorry, this goes up to 450. I should have read that better. 450. Then it goes down 350 to 100. So this value is 100. And then what happens? Look carefully at this. This is the applied moment here of 1200. And our rule is if it goes in the clockwise direction, moment takes a step up. So what we would do is then draw this discontinuity up like this to a new value of 1350 or 1300. Yeah, it's 1300 because it starts with 100 and then it goes up here, so that'd be 1300. From there it goes down 350. We have a 350 negative right here, so it goes down 350 to the point where this is now 950. And then we know that this is now negative. Again, these are all decreasing because the shear is negative. So it goes negative, negative, and then it goes down another 950 down to 0. And that's our final moment segment. Where's the maximum moment? The maximum moment in this case occurs where that applied moment is. So in this case, but there are peaks where wherever shear crosses zero, there's a local minimum. So right here, where shear crosses the zero, you'll see a local maximum in the moment. And obviously, because it's got that applied moment right there, we have a large moment right there as well. Well, in this next one, we're going to talk about uniformly distributed loads. And in general, when you have a uniformly distributed load pointing down, shear will decrease linearly between that. All right, so let's first find the reactions. I have an AY here and a BY here. And I've solved for those reactions right here. So let's just draw the shear diagram. AY is, well, first of all, this is negative 300. That's where it starts. So it goes down negative 300. Then over here is zero change. Then it goes up 750 to get up to something like that. So let's start with negative 300. Then again, it is uniform or steady, as I would say. It's not changing anything between that. It's going to go up by the value of AY, so up 750, so that would go up to 450. Now here's where it decreases linearly, and I'm going to just kind of draw this in here in a light red line. I don't know for sure where it's going to go, so this is the slope is downward 1200 newtons per meter, and we're going to get to that. But what I'd like to do is jump over to the right side of the graph, and let's see if we can do something here. I know that the shear ends at zero, and I know that I have a applied load here which goes straight down to end at zero. So I'm just going to do that. Put that negative 600. I know that's where that goes. I know there's no change between here and here, but I know that BY goes way up by 1350. So it goes up like this from this point. Now this is positive 1350, and this had to get up to 600, which gives me a value down here of negative 750. Okay, so now I have 2 points that I can connect. And let's just do that. I can see that this goes straight down like that. And in the middle here is where the shear crosses the x-axis. Now, let's find out an equation for this line. And that's pretty easy. It's a straight line. And I know that straight lines have a y is equal to mx plus b kind of thing. So let's just say that the slope is going to be the value of the shear. The slope is the value of the distributed force. So I can say that V between A and B, or between any place here, but between A and B, is going to have this function. It's going to say the shear is equal to what the shear is at the beginning minus 1200x. Okay, so here's my shear equation. V between A and C, or between A and B, is equal to 450 minus 1200. Now I'm going to label this point right there C, because that's kind of that's a key place where things cross the x-axis. So let's just find out what that looks like. Where it crosses the x-axis, if I want to set this equal to 0 because shear is equal to 0, my equation is 450 minus 1200x. At C is where shear is equal to 0, and I can solve that for this distance. D is equal to 3.75. So this one is, or 0.37. So this distance is 0.375 meters. Okay. With that, I can draw some areas, or compute some areas, and then I can draw the moment diagram. So let's compute the areas over here. This one is A1, and that's going to be equal to 300 times 0.5 is going to be 150. This one in here is a triangle. That's 1/2 BH, so 1/2, the base is 0.375, the height is 450, and so that is going to be 84.4. This distance here, or this area here, is also 1/2 BH, and you can compute that to be 234.4. Then over here, this one is just a rectangle. This is just going to be BH, and so that one is going to be 600. All right, now that I have the areas under the moment diagram, let's draw the, under the shear diagram, let's draw the moment diagram. So again, negative shear means moment decreases. Positive shear means moment increases. If this is a straight line or linearly decreasing, moment has an inverted parabola shape. Where this is positive, moment increases. So I can just tell by looking at it what the shape is going to be. So let's just draw it. I know it's going to go down this way. I know it's going to have a quadratic shape like this. Then I know it's going to go down this way because this has to be going up like that. These are the things that are going to, or the positions that are going to be lined up, and where this goes right there, they will get our maximum spot. Now let's go ahead and put in the numbers because we can read those off of the shear diagram. So this goes down, the change in moment will be 150, so this is minus 150. The change in moment here is positive because this is positive. Because this is positive, it's going to go up a magnitude of 84.4. So I can compute this distance, or that position, to be 65.6. Then I know that this distance here, or that area here, is 600, so I know just by inspection that it goes down to negative 600. And now we have a shape of the moment graph. Did I do that wrong? Yes, I did that wrong. This is actually 300. Sorry about that. This is actually 300, so this is actually 300. Yeah, I'm sure many of you caught that when I was writing it down, but I corrected it here before we left the page. Well, this next one I want to do is very similar, and I've already done all the work here, so I'm just going to, I've shown all the work here, so I'm just going to talk you through it. All right, so here I have a uniform beam, or a simply supported beam with two uniform loads. This W, or this weight, is equal to 10, which means this one is equal to 20. I'll go ahead and put those on there. 10, and this is 20. Then it says L over 2 is equal to 10 feet, so this is going to be 10 feet and 10 feet. Okay, let's find the reactions. Again, I didn't do that, didn't write that down, but you can do that. Let's draw the graph. All right, once I have that, once I have the reaction of AY, I know it goes up 125. Now let's just jump over to BY. I know that it goes up 175. That's the way I would probably start. From here, I know that the shear starts at 125 and goes down at 10 feet per, or 10 pounds per foot. Okay, that is a negative 10 as it goes down. So what I'm going to do is write this equation for this line. I'm going to say that shear is equal to 125 minus 10x. And at this point, where x is equal to 10, I can find out what that value is. So that's what I did. At x is equal to 10, the shear is equal to 25 right there. And now what happens from here? Now these are lined up. From here, I have a new equation. It says from here down to here, I have shear is equal to 25 minus 20x. So let's just jump down here. Shear is equal to 25 minus 20x. And then I can, now that I have the shape, I can start computing some areas. So let's just do A1. This A1 is a triangle load, 1/2 BH. So here we go, 1/2. My base is 10. My height here, because that is 25 and that's 125, this height is equal to 100. A2 is just uniform, so it's BH is equal to 250. A4. Let's go over here to A4. Well, actually, I can't do that quite yet. We have to find out this little distance x, which is a very common problem that you'll have to figure out. You have to figure out where the shear crosses the x-axis, which means you need to have that little distance. So again, what I've got is a shear equation, 25 minus 20x. And here I want to solve this where shear equals 0. So as shear is equal to 0, x right here from this equation, solve this for x, and I get x is equal to 1.25. So that's where that crosses there. Once I do that, I can start solving for the areas. So this one is a 1/2 BH. It is a triangle. That area is going to be 15.63. Then you have to compute this distance here. It would be 10 minus 1.25, so that's 8.75, and then the area here is 1/2 BH and 765. So here are all my areas, and those give you the magnitude of the change in the moment diagram. So I'll start at 0. I go up to A1 plus A2. And again, you don't have to do them separately. You can kind of add them together. The exact shape is not as important as the points that, or the transition points of where you get there. So anyway, between A1 and A2, I go up to 750. Then here I just have this one little graph, and I know that this is where the maximum is. So 750 plus, where are we? 15.63 gets me 765.6. That's the peak moment. From here, the shear is negative, which means the moment decreases, and then it decreases this same amount of A4. And it turns out that's the same amount, 765.6. I computed it this way, got 765.6, and it's the same as the A4 if I would have done it that way. So again, more than one, maybe you're not being able to see all that. More than one approach sometimes on how to do this, but a key takeaway is trying to find this little distance, that little point at which the shear crosses the x-axis, and then knowing that where it crosses the x-axis is where most often your maximum moment occurs.